Have you ever wondered if you could predict the future? I don't mean with a crystal ball or anything like that. I mean with math. Well, today, we're diving into something called differential equations. Think of it as a kind of secret language that our world runs on, describing everything from a cup of coffee cooling down to how planets move through space. It's going to be fun.
So, yeah, that's the big question, right? How can we predict what's going to happen next? And look, math isn't going to tell you the winning lottery numbers, but it can predict how all sorts of systems around us behave. The trick isn't magic. It's just about understanding the rules of change.
And to get our heads around it, let's start with something super familiar, your morning coffee. You pour it, it's hot, and you know it's going to cool down. But have you ever really stopped to think about how it cools? Believe it or not, the secret to predicting some pretty complex stuff is hiding right there in that mug. That cup of coffee is just one small example of a much, much bigger idea, that pretty much everything in the universe is in motion, constantly changing. And if we can understand the rules for that one cup of coffee, we can start to understand the rules for planets, populations, you name it. It's all about the dynamics of change. Now, think about it for a second. The coffee cools down really fast when it's piping hot, right? But as it gets closer to room temperature, that cooling process slows way down. And that's the whole key right there. The rate of change isn't constant. The speed of cooling is itself changing. Your standard high school algebra just, well, it can't really handle that. We need a totally different kind of tool. So, to describe a world where even the rate of change is constantly changing, we need a special kind of mathematical recipe, one that's built from the ground up to capture the process of change itself.
And that, my friends, is a differential equation. At its heart, it's just an equation that has a derivative in it. And derivative is just the fancy calculus word for rate of change. So for our coffee, the equation basically says, how fast the coffee is cooling right now is directly connected to how hot it is compared to the room. Simple as that.
Think back to the math you first learned. An equation like area equals length times width, that's totally static. It's a snapshot. It describes a fixed state. But a differential equation, it's dynamic. It describes a process, a story unfolding over time, like our coffee cooling down. It's the rulebook for how things evolve. That's why I love thinking of it as the universe's recipe book. If you can figure out the differential equation for a system, you've basically found the secret recipe that dictates exactly how it's going to behave from one moment to the next. It's like its operating manual. Now, an idea this powerful didn't just appear out of thin air. It was built piece by piece over centuries by some of the greatest minds in history who were trying to solve the biggest, toughest problems they could find. It really kicks off around 1675, when Leibniz gives us the notation for calculus, the language we need to even talk about this stuff. Then you get these brilliant guys, the Bernoulli brothers, who start using these new tools to solve real-world puzzles, like the exact shape a hanging chain makes. And by the mid-1700s, the absolute genius Leonhard Euler comes along and turns all these clever tricks into a systematic, powerful field of mathematics. Okay, so what can we actually do with this incredible mathematical language? This is where it gets really fascinating. Having this recipe for change gives us what you could almost call predictive superpowers. Let's get practical. Picture a crime scene. A detective needs to figure out the time of death. Well, a body cools down in a predictable way, just like our cup of coffee. And guess what? There's a differential equation for that. It's called Newton's law of cooling. By measuring the body's current temperature and the room temperature, they can use that equation, solve it, and essentially rewind the clock. And when they solve that equation, bam, the model gives them a time of death approximately 8:18 p.m. This isn't just a wild guess. It's a prediction that comes directly from the mathematics of change. But this idea, this recipe for change, is so much bigger than just temperature. The same fundamental thinking can be applied to all sorts of other systems that change over time. Let me show you what I mean. So what's this big number all about? This is a different kind of prediction. This number, 383,725, is the predicted population of a community 40 years from now. How? It's calculated using a differential equation that models population growth, often based on the idea that the rate of growth depends on the current population size. For anyone in city planning or managing resources, that's an incredibly powerful number to have. And it works backwards in time, too. The exact same principle is behind radioactive dating. The rate at which a radioactive element decays is predictable. By solving the differential equation for that decay, scientists can look at an ancient fossil or artifact and figure out its age, sometimes with amazing precision. They are literally using this math to look thousands of years into the past. So you see what's happening here? We've used this one core idea, this recipe for change, to solve crimes, to predict the future of cities, and to date ancient history. It's not an exaggeration to say this is the language of our dynamic, ever-changing world. And its reach is just breathtaking. We're talking about the same fundamental math being used to model the airflow over a jet wing, how medicine spreads through your body, how electrical circuits behave, the trajectory of a rocket, how financial markets might move, and even how earthquake waves travel through the Earth. It is a truly universal tool. I think this quote really captures the magic of it all. Without this framework, you're just looking at a jumble of meaningless data points. But once you find the right differential equation, you can transform that data into a powerful model that can actually make predictions. And that leaves us with a really big, exciting question. Our world is just this massive, interconnected web of dynamic systems, from the climate to the economy to the spread of ideas. So if we can just find the right recipe for change, the right differential equation, what else about our future could we unlock? What else could we predict?